This is our Team 15 paper presentation, and the paper is called Geometric Correspondence Network for Camera Motion Estimation. Based on the paper, this is the outline of today's presentation. Okay, now let's start with the introduction. So, this paper is about the task of camera motion estimation by focusing on visual odometry, or called VO, which means that it is the frame-to-frame motion estimation using information from a vision sensor or camera. This paper created a new framework called GCN, or also called Geometric Correspondence Network, which is a combination of both CNN and RNN. CNN, which means convolutional neural network, and RNN, which means recurrent neural network, to perform both key point detection and feature descriptor generator, which is the main point of visual odometry. And on the picture, we can see that there is an example of detecting the key points of a person's face. As what the model names or the framework name, it is called geometric correspondence network. So actually, this optimized on geometric correspondence instead of the semantic correspondence. To train the network, the ground truth is obtained by obtaining key point based on the high gradient point in the image. So what this means is that the key point that we saw in the previous image is obtained based on the intensity change of the color in the image. And we can see later on that this paper uses Harris algorithm. Now we move on to the related work. So for the related work, there are three different methods, which is sparse, dense, and using neural network. Sparse method is that we will extract the key point first and then match it based on the geometric constraints and local descriptors, which is very different with the dense method, as will be mentioned in the later slides. And so what is the example of a sparse method? It's ORB SLAM and ORB SLAM 2. Um, ORB SLAM is, as we all know, it's extract feature from real time using ORB in this frame, and then are then matched to the recent frames to perform camera motion, and then to distant frames using a binary back of word representation to detect loop closure. And the implementation of this paper is very related to ORB SLAM. The difference is that ORB SLAM uses an off-the-shelf feature and design a complete pipeline around it, while the paper focused more on on extracting the feature itself, which complement ORB rather than competing with it. Now on to dense method. In dense method, information from all of the pixels in the image are used, which eliminates the need for feature detection. And the example of dense method is kinetic fusion, continuous elastic fusion, which builds a volumetric representation to which new frames are matched. And another one is RGBD-TAM, which is a combination of both semi-dense photometric and dense geometric errors for post-estimation. Now, this is a new method which combines the previous two traditional methods with neural network. For an example is called UCN, or Universal Correspondence Network. It extracts dense features for applications with neural network where one needs geometric and semantic correspondence. Another example is called FlowNet, which uses CNN, or convolutional neural network, which is trained by a large synthetic dataset to directly predict per pixel flow. This is actually related to also the paper's work because this uses optical flow and it can be used to estimate the camera motion too. However, our paper focuses more on detecting and matching the points that are best suited for estimating the camera motion. The next one is about motion estimation and its algorithm. This part discusses about bundle adjustment algorithm, which is also called BA, which is a traditional algorithm for camera motion estimation. Now we first assume that we have two images, which is the reference and the current image, like the picture below. So the current image is a bit slightly to the right, and the reference image is the normal image. We want to align these two images. Aligning these two images means that we want to connect the reference image with the current image. For example, this red dot with the green dot. Because if you see here, this image from the edge to this point is different from this image edge to this point. So first, we have to find out how to transform the reference image to the current image by first defining a warping function, this warping function, to project a point, this one say xi, this one is xi, to 3D coordinate. With that previous function, we will project the current image to 3D coordinate. So this one will project it to 3D coordinate. This is the 3D plane. And then after that, we warp the projected 3D points using rigid body transformation into another point on the 3D plane. After that, we want to project them back to the 2D plane. So this point here, we want to project it back to the 2D plane. And then, so the goal is to minimize the error of the red dot and the green dot. And this is what we got, the red dot. And then, but then like on the previous slides, this is the one that we want to get. So we want to make this smaller, like minimize these errors, which can be calculated by the mean squared error of this point with this thing is from this point. We want to minimize the red and green dot, like I said in the previous slide, by solving this equation. But first, we have to know that the rigid body transform matrix is part of the Lie group SE3, which is this one. So, and then the Lie algebra SE3 with small s and small e can be mapped to the Lie group big S, big E3 using the exponent function. So that's why from this you can get this, which is the Lie algebra of C, which is this W omega is the skew symmetric matrix of omega. We can now rewrite the minimum error problem that was in the previous slide into this equation because we already have the C, and then we only have to calculate the Jacobian matrix with respect to the residual measurements. And then we can solve this using Gaussian-Newton method to solve the nonlinear least square problem.
Now we'll get into the proposed method. And this is the overview of the proposed method. As mentioned before, this paper combines CNN and RNN to learn how to obtain the key points and its feature descriptor from a sequence of images. And the input will be two consecutive images taken from a sequence of images which will be denoted as image 1 and image 2. Now we'll go through the first step, which is the CNN part. They use pre-trained ResNet 50 as the convolutional network, and the reason why they chose ResNet 50 is because it has good performance and can still perform in real time based on their small experiments they did using the Kitty raw dataset, which shows on this figure below. And the bar represents the overall matching accuracy, which we can see at the plotted percentage on the left hand side, and the green dot is the number of parameters which correspond to the right hand side of the y-axis. And in this experiment, ResNet 152 get the best performance, but as we can see over here, the number of parameters is twice than the ResNet 50, which they said it cannot perform in real time, and that's why they use ResNet 50 as the backbone of the convolutional network. And let's go to the CNN process. First, those two images, image 1 and 2, will be fed into the pre-trained ResNet 50 and we'll get a lower dimensional representations, feature representation. And this representation will go to the convolutional network to reconstruct into the original image size. And during the deconvolutional, instead of using the normal architecture to reconstruct the image, the author mentioned a shortcut with the intention to obtain more fine-grained features. And this shortcut will take the feature maps of the image obtained during the convolutional process and combine the output by summing up the value over the corresponding channels. and the author said that this trick will obtain more fine-grained features. And for the loss function, they use the triplet loss with L2 distance or the Euclidean distance, and this loss function is commonly used in deep-metric learning tasks. For the notations, here we got xi, which is the anchor point, yi star the positive point, zi star the negative point, and as xy is the L2 distance between two factors at location x, y, and the m is the margin, which determine how far the different samples should be pushed away in the feature space. And using this triplet loss function, it will let the network learn the feature representations so that the distance between the anchor and the positive sample is minimized and the distance between the anchor and the negative sample is maximized, which is this part. Here we will talk more detail about those 3 points which will be used to compute the triplet loss. First is the anchor point, which is the key points of the image 1. Next is yi, the positive match point in the image 2. And to obtain yi, it uses the warping functions which we have already explained in the motion estimation part. And it basically just plot the 2D key points of the image 1 to the 3D coordinates and do the transformation using the given rotation matrix and translation factor to get the 3D coordinates of the image 2, which is the target image, and then convert it back to the 2D coordinates. And that is how we get the positive match points. And the last one is the the negative match point in the image 2. So it is simply the key points of image 2 that is not included in the positive samples, but with the smallest distance. It mentioned in the paper that the other points other than the smallest distance can be used, but in their experiments, the closest points will contribute the most to the loss function. In RNN, the network will learn in both spatial and temporal information, and it uses bidirectional recurrent convolutional network. As shown in the figure, the hidden state and the output layer can be obtained by the equations on the right-hand side, and the initial weights are all randomly initialized. So, first it will compute the hidden state H by concatenate the feature maps that we've got from the CNN network with the previous hidden state. Here is H0, and then convolve it with the input to hidden weight and use the ReLU activation function in the end. And it is the same for computing the next hidden state, the H2. Next is the hidden state V. It is basically the same as computing hidden state H, just with different directions. And instead of using H, it uses V as the hidden state. Last is the output layer. It will sum up the output of these two, the green and red, and then apply the softmax activation function. For the loss function, it sums up the cross entropy for key point of image 1 and cross entropy for positive key point of image 2. And since it will be divided into two classes, 0 and 1, 0 is for not key point or the black color in the mask image, and one is the key point, the white dot in the mask image. And to balance the weight of those two classes, they've got the alpha parameter, alpha 1 and alpha 2, to balance the different classes. And it's set into 0.1 and 1. This one is for the key point class, and this is for the not key point.
Now we'll go to the implementation detail. And to generate the dataset, it uses TUM dataset, which is indoor scenes with semantic informations. And for the training part, it uses the dataset with FR2 prefix. And for the testing dataset, it uses FR1 and FR3 prefix to ensure there is no overlap. After that, they do the subsample by selecting only every fourth image in the sequences and to let it more different. And to generate more key points in the images, the author applied the Harris algorithm twice. First, they apply it in the whole image, and then they divided the image into 4 times 4 grids and apply it one more time in the sub-image. Now we'll go into the experiments part. This is the experiment result without using the loop closing, and is conducted using only TUM dataset, which are indoor scenes of different offices. And absolute trajectory error, or ATE, is used to evaluate the result. As shown on the table, GCN outperformed other methods by achieving the best performance of all of the tested scenes, especially in the last row, the FR3 and then F scenes, which contains weak texture wall, and GCN can still successfully extract the features. And the author did another evaluation using Kitty raw dataset, and there is two versions of GCN provided, GCN2M and GCN Kitty. GCN2M refer to the same model as the previous slide, which called the GCN. The other version is called GCN Kitty, and it is fine-tuned using the Kitty dataset shown at the table above, and only the bold font is used to fine-tune the new version of GCN. But it mentioned that the author used the whole Kitty training dataset to train the UCN, which is the baseline, and all of them are compared using the same dataset. From the table below, it shows that both GCN-TUM and GCN-Kitty outperform the non-learning and learning-based method, and GCN-TUM has the best result even when tested on visually different from its training data. However, GCN-Kitty didn't perform better than GCN-TUM, despite the fact that it is fine-tuned with more dataset than the GCN-TUM, and the author speculate that this might happen because it is trained on smaller subset of the Kitty raw dataset compared to UCN. Last is the evaluation using closed loop system. And for the closed loop system, the author implemented a lightweight SLAM from open source SLAM framework using the key point extracted using the GCN and compared it with the other methods. And first row shows that GCN and or BSLAM2 obtained a competitive result, whereas the other method is struggling because that scene FR1 floor dataset contains missing frame, which causes large displacement between frames, and it also contains a lot of flat structures. And next is the FR2 large cabinet scenes. Orbis lamps encounter tracking issue in this scene is because it looked at the white back of the cabinet and failed to obtain the features. And in FR3 and then F scenes, all of the baseline cannot perform well because of the weak texture wall, but GCN can still perform nice performance.
Now, the summary and conclusions. To summarize, this is a new framework with neural networks to learn both key points detection and descriptors optimized for camera motion estimation. Then, training data is generated using SLAM benchmark datasets, which uses the FR2 prefix dataset with ground truth camera information, which is the rotation and translation of frame to frame. The results from the experiment demonstrate superior performance compared to the current existing method, even with minimal loop closure optimization. The target application is for fully autonomous flying robots, but the papers mentioned that it should be able to generalize for other autonomous robots. Future plans involve improving efficiency by reducing network depth and storage consumption with accuracy as the trade-off, as demonstrated in deep compression or squeeze nets. Additionally, the paper also proposes exploring the potential of using representative binary features for matching, as seen in DeepBit. This enhancement will be able to make the framework more suited for real-time applications. Now, the last part is about our insight after reading this paper. So for the insights, one of the thing that we got is that the paper's notation is a bit confusing because so on the proposed method part, which is on the recurrent network, so it is said that in the paper that this part is saying that the ground truth is a mask of 0 and 1, where 0 means it is not a key point and 1 it is a key point. And then a weighted cross entropy, which is this formula, is calculated over every pixel. Um, however, so this formula um like has this description where so first CCDC is the label of a given 2D point, which I presume is the ground truth, and O is the predicted key point. So this is our prediction, and then XI and YI are key points and their correspondence obtained by warping. YI it's on the previous section, but so we won't discuss YI. But so let's just look at the XI for now. And alpha is a parameter to balance between different classes. This is just parameters to balance it. So the thing that I think is a bit confusing is because so first of all they say xi is a key point. So cxi means that it is a label of a key point, which means it should be one every time. So if that's the case, that means the second part of this formula is always zero. So what I think it should be is that instead of cxi, it should be ci because it is iterated over every pixel here, and then instead of oxi, which is the predicted of a key point, it should be like this is the input of like every pixel, and then after that there's an output and that is fit into a sigmoid function, which is should be oi instead of oxi, and then it is the output of the ith featured pixel when it is fed into the rcnn, which is the recurrent convolution neural network. And I think that's it. So the next insight is that this paper only discusses using rigid body transformation, which is made up of only translation and rotation. However, is it possible to make the method extendable towards scaling? So for example, it's for the data set where the motion is not only rotational and transitional, which is left, right, or rotated, but also like movement for forward and backward. And then the next one is that it's about the experiment part in the paper. So the author mentioned that GCN Kitty is lacking compared to GCN TUM. And the reason for this is because GCN Kitty which is a fine-tuned model of GCN TUM, is only trained with only some parts of the Kitty dataset. This reasoning does not make sense because GCN TUM only uses the TUM dataset to train, and it is not fine-tuned with the Kitty dataset at all. So I think that we think that the outer reasoning for why the GCN Kitty is worse compared to GCN TUM is not a good reasoning. That is the end of the presentation. Thank you.